Hi everyone, I'm Vignesh Menon, a PhD research scholar in Christian Doppler Laboratory, ATHENA at University of Klagenfurt, Austria. Welcome to the presentation of the doctoral symposium paper titled Video Coding Enhancements for HTTP Adaptive Streaming. This work is supervised by Dr. Christian Timmerer from University of Klagenfurt, Austria. In this presentation, I will introduce the premise of this work, the research question we try to address in this research, and the ultimate target of this research. We shall discuss a few outcomes so far and summarize the work so far. Video streaming over the internet makes HTTP adaptive streaming necessary. It is to cater to a wide variety of devices, network speeds, and user preferences. Each video sequence is split into multiple segments which are encoded at multiple bitrates, resolutions, and codecs. They are delivered to the client based on the device capability, network speed, and user preferences. In terms of video coding, HTTP adaptive streaming can be visualized as shown in this figure. The raw video is encoded at multiple times for multiple resolutions and bitrates and then sent to the network. The client has a decoder which decodes the corresponding video and it plays on the display. This brings us to the first research question: how to efficiently provide multi-bitrate and multi-resolution representations for HTTP adaptive streaming. The amount of ultra-high definition content and high frame rate content is increasing day by day. More devices from various manufacturers are being introduced, like high-resolution televisions and mobile phones. Hence, more representations need to be encoded in the server to cater to many devices. The goal here is to reduce the encoding runtime in the servers while maintaining similar compression efficiency. This figure shows a pictorial representation of the normalized encoding time of 12 representations encoded with X65 HEVC encoder at multiple bitrates and resolutions. It is observed that as resolution doubles, the encoding time also doubles. Furthermore, it is observed that many encoder decisions like block partitioning are redundant across representations. This calls for efficient multi-rate and multi-resolution schemes to share the encoder analysis information across representations. There has been some works in the literature which tries to address this research question, like limiting the block partitioning search levels, reuse of additional available information to help with other encoding decisions, and there has been also some multi-encoding methods which combines both multi-rate and multi-resolution encoding optimizations. The second research question is how to efficiently provide multi-codec representations for HAS. Currently, there are multiple types of clients. Some support only old codecs like AVC, some support only the latest codecs like HEVC or VVC, and some support all of them. Hence, to cater to all devices, the server has to encode in many codecs, which adds to the computational load. Similar to the first research question, here we try to reduce the encoding time of representations without compromising the compression efficiency. Now, moving to the third research question, how to improve the encoder performance using content adaptive algorithms. In this research, we have doing a quest to achieve a perfect trade-off between the perceptual quality and compression efficiency. This is the basis of content adaptive encoding, where we allocate only a few bits for a given video based on its complexity, which effectively can have significant bitrate savings. In this research question, we tend to derive and content adaptive spatial and temporal features for a video, which we might later use to influence encoder decisions like a slice type, condensation parameter, block partitioning, frame rate, resolutions, and much more. Some tried out approaches for content adaptive encoding are short detection, content adaptive block partitioning, content adaptive condensation parameter estimation. In terms of streaming, per shot and per title encoding schemes are also introduced. The fourth research question is how to improve the efficiency of per title encoding for live streaming applications. In live streaming, the encoding time is constrained to ensure zero latency or low latency. But generally, encoders have presets, that is, set of encoding parameters with conservative settings biased towards compression efficiency. In this research question, we try to reduce the time taken to compute the convex hull in per title encoding by estimating it using certain spatiotemporal features. We also study how to dynamically configure the encoder presets to sustain a given target encoding speed. Based on the 4 research questions, we envision a video compression framework for HTTP adaptive streaming as shown in this figure. The inputs are the target encoding time or target encoding speed, the maximum quality of representations, the target average difference in the quality of representations, which is denoted as JND, which is just noticeable difference, a priori information like the encoder or the codec used. Based on the video complexity features extracted and the input parameters, an optimized encoding bitrate ladder is predicted. The encoding is done only for the selected representations where multi-encoding schemes are used to accelerate the encoding. One of the outcomes of this doctoral study is VCA, which stands for Video Complexity Analyzer open source project, which was released in February this year, which is a practical implementation of the video complexity feature extraction envisioned in this study. Weighted DCT energy-based features are extracted at a rate of 370 frames per second for ultra-high definition video content with 8 CPU threads, which utilizes x86 assembly and multi-threading optimizations. In this figure, we show how VCA can be used in content adaptive encoding systems, where for any input video, firstly, it is passed through the video complexity analyzer, that is VCA, and it generates some analysis stats, which are the spatial and temporal features, which is fed into the encoder, and it uses these values to make decisions accordingly. Another outcome of the study is perceptually aware bitrate ladder prediction, where bitrate ladder is predicted for a given video such that there is a perceptual quality difference of one just noticeable difference, JND, as shown in this figure. So here we observe that there is always a gap of one just noticeable difference across different representations. So the figure on the left shows the schema for the perceptually aware per title encoding scheme, where a set of resolutions supported by the streaming service provider, the maximum and minimum bit rates, the maximum target quality, the target JND, and the encoder used are passed as the input parameter. And based on the video complexity features and the input parameters, optimized bitrate ladder is predicted. Another outcome of the study is the dynamic frame rate prediction, where the frame rate is determined based on the video complexity and target bitrate. The video is temporarily downsampled based on the prediction, encoded, and then sent to the network. On the client side, the video is decoded, temporarily upsampled, and then displayed. So in the interest of time, I have just briefly described 3 of my papers so far, but this table summarizes the work done so far for this doctoral study. Now, thank you for your attention. I am happy to take any questions and receive feedback. Thank you.